Morning, everybody. Thank you for the kind introduction. And first, I would like to thank the organizers of this conference because it's very exciting and also it is in such a charming place and environment. So my name is Franca Albertini. I'm from the Institute of Materials for Electronics and Magnetism in Parma. And my work will be mainly focused on metamagnetic Heuslers. And I will discuss a path of research from bulk to nano and of these materials that have many multifunctional properties, mainly exploitable in energy and smart applications. And in this path, of course, our main goal is to obtain good materials to be exploited at the nanoscales in micro and nano devices, but also by studying very oriented and very well-engineered nanostructures. We have been also able to clarify some properties of these materials that can be used also for bulk applications by studying the interaction at the different length scale between magnetism and structures. And also we have obtained a nice structure, magnetic structures that thanks to the Martensitic microstructure are very flexible and we can engineer the magnetism and the magnetic patterns of these materials by simple external stimuli or by preparation methods. So maybe I use this. Okay, so the main properties of these materials, multifunctional properties, are provided by two main physical properties of this class of materials. These are full Heusler compounds, mainly nickel-manganese-based, with another element of the main group that can be gallium or indium, tin, antimony. And these materials have these two important properties. The first and the main is a Martensitic transformation, that is a diffusion-less solid-state transformation from a cubic high-temperature austenitic phase to a less symmetric, let's say, to a tetragonal or orthorhombic or monoclinic low-temperature Martensitic phase that depends on the composition. On the other hand, these two phases can be magnetic or non-magnetic. Here, for instance, in these thin films of nickel-manganese-gallium composition, we have a direct transformation for a ferromagnetic monoclinic martensite to a paramagnetic austenite. But, and we have a huge change of magnetization of these materials that can be tuned at different temperatures. Indeed, these materials are very nice and flexible because we can make many compounds by changing the relative composition between the elements and also by making possible substitutions. And in fact, sorry, but okay. In fact, for instance, here you can see that as we have here a first Martensitic transformation from the two phases followed by the Curie transition, we can, by changing composition, we can merge the two transitions, and also by changing the elements, we can have different kind of transition. First, a low magnetic martensite, then we have no magnetic moment, and then by increasing temperature, in this case, we have an increase of magnetic moment. So we can tune this change, huge change of magnetization from 0 to the maximum or the opposite by temperature and by changing the composition. Here, for instance, in these diagrams, there are entropy versus temperature plot, and in correspondence to this transition, we have magnetocaloric effect. In this case, it's a direct magnetocaloric effect at the first order transformation. Here we have an inverse magnetocaloric effect at the first order transformation, and followed by a direct magnetocaloric effect at the Curie transformation, Curie transition. They were introduced and they have been studied for about 20 years. There have been a big effort on these materials, mainly for this application. In fact, they have big promise, and also they have huge effects. already at the beginning of, in 1996, they were introduced, and after really 4 years, the 6% of strain was found in these materials induced by magnetic field, a field that we can obtain by permanent magnets, and also we can reach now strains exceeding the 15%. And this magnetomechanical important feature is linked to the Martensitic, to the microstructure of Martensite and to its manipulation by magnetic fields. Then we can have also other magnetomechanical effect induced by field, by inducing the transition by field. Then other properties have constantly arisen along the years: magnetocaloric effect, inverse magnetocaloric effect, baro and elastocaloric effect, that is caloric response of the materials to pressure or stress. But there are many still open questions, both on the basic physics and also on the full exploitation of these materials. One is that in polycrystalline material, the effect is much lower, so it's needed to study the role of microstructure in these magnetomechanical properties. For inducing this second magnetomechanical properties, we need high fields. And there are many reversibility issues because the first order character of the transition prevents the full exploitation of the material in the cyclic inducement of the transition by an external field. And also there are poor mechanical properties. More recently, the multi-stimuli application on these materials has been proposed for the multicaloric exploitation that allows to apply in a consequent, to apply different external field at the same time, that may be magnetic field and pressure. This application can be simultaneous or sequential, and they have been used to increase some of the multifunctional properties. For instance, the simultaneous application of field and pressure has increased the magnetocaloric effect. The sequential application can be used to reduce the hysteresis and apply and fully exploit these materials, or also they can be exploited in a multicaloric and more efficient caloric cycle. The phenomenology arises from the coupling between thermal, mechanical, and magnetic properties. You see, if you apply a field, you can change entropy and temperature, or if you apply stress, or both at the same time, you have you change in the other properties. And so this is very important. And now with the multi-field exploitation, there are many other studies and many new measurements and the models to also to verify and to understand the interplay between these degrees of freedom. And in our group, we have been working on these materials for many years. The first aim was to design new compositions with increased discontinuities in these properties in order to make materials more flexible to external stimuli. If we have high magnetization change at the transition, they are very sensitive to the application of magnetic field, and then we can change all the other properties. In addition, the combined use of magnetism and the conventional shape memory, that is a property of these materials, may open other important applications, mainly in the field of solid-state refrigeration, thermomagnetic generation, so thermal energy harvesting, mechanical energy harvesting, and also in actuation and sensing. Very important, as I already mentioned, is the microstructure of these materials, that when we have the transformation from austenite to martensite, we have the martensitic microstructure that is a 3D pattern of interrelated twins. So it is possible, in principle, to engineer the microstructure from the atomic, the atomic scale to the microscale by exploiting the connection and interrelation by the different twins. Also the magnetic field induced reorientation, that is the property that gives the name to this class of magnetic shape memory materials, is due to the reorientation of twin variants by the application of magnetic field. Here the ingredient is the high magnetocrystalline anisotropy of these materials. And if we have a material, as in this sketch, made of two twins, by applying a field, it's more energetic favorable to move the twin boundary and increase the quantity of materials aligned with the field than to reorient the magnetization. So for this reason, we obtain huge strains. And the magnetic field manipulation of microstructure is at the basis of this phenomenon that reaches more than 12% in suitable fields. So the microstructure plays a primary role in all the thermomagnetomechanical properties, but also it's important for the multifunctional properties arising for the cyclic application of external field, because it influences the Martensitic transformation path and the hysteresis. And, okay, this I've already said. Going to our work of today, we have starting from bulk material, and after selecting a good composition, we have studied thin film that have a great potential for the integration in active microsystem, and also for the realization of micro-nano devices that could be energy harvester, micro-refrigerator, or actuators. And we have produced epitaxial thin films of different thickness and on different substrates. Then we have moved to pattern micro and nanostructures that is still almost unexplored field. And from that, we have also detached this patterned material from the substrate in order to obtain the freestanding materials that are materials with a simple design, and they could be used as a machine and for many applications, and including the bio applications. We have also followed another path in our research due to the need of material and in large quantity and with very repeatable properties for the magnetocaloric application. We have set up a technique for producing up to 250 grams of magnetocaloric materials. In this case, it was the giant inverse nickel manganese indium gallium. And then we have also made some study on the on powders obtained by ball milling, and in order to produce material with good magnetic and Martensitic properties, and can be used to composite production ferrofluids and in solid refrigeration materials, functional materials. I will mainly focus on this part in this talk, and starting, from this part, what we have done from thin film, we have engineered the microstructure during growth and after growth, and we have made a multi-scale investigation of fundamental relations and studied microstructure-related effects on the Martensitic transformation path. Then the patterned structure have been mainly produced to unveil the effect of lateral confinement and geometry on microstructure and magnetism of these materials. And as for the freestanding nanostructures, We have studied the effect of substrate release, and also we have verified a magnetothermal actuation of these freestanding materials. As for the microstructure engineering, you have exploited the substrate, and in case of chromium MgO, we have exploited the expansion due to the substrate, and in this case, we can select a kind of twins. In this case, it's a Y type of twins, and in the Y type of twins, the magnetization lies in the plane of the film. So by selecting the twins and by exploiting the flexibility of the Martensitic microstructure, we can select the orientation of magnetization. This is for thin films. For the film of the same thickness grown on MgO, when there is an expansion due to the, here is compression due to the substrate, we obtain another kind of twins that are the X-type, and in this case, the twins lies in this direction at 45 degrees, and also the magnetization points in and out of the plane. In fact, in the magnetic force microscopy measurement, we can detect some magnetic domain. By changing the thickness of the material, we have obtained 214 more than 100 nanometer and 200 mixed film with X and Y microstructures. These regions are characterized in this case from the magnetization in field, and in this case from the magnetization out of the plane. And by applying a stress during the growth, we can also obtain an isotropic pattern, so these lines along certain lines induced by the stress of the substrate during the growth. This is interesting because magnetic force microscopy is a very easy tool to detect the orientation of magnetization and to study also the corresponding microstructure. In case of X-type variants that have a higher roof-like type corrugation, we have perpendicular domains, while in the case of X-type variants that have a magnetic moment in the plane, we don't have a signet, but only some domains, walls inside. By checking magnetic force microscopy, we can immediately see what is our magnetic pattern. The orientation have been checked with electron holography that has allowed to correlate the magnetization orientation with the twin and the microstructure of these materials. And we have gone on with by exploring the possible microstructure engineering. So by changing the thickness and the underlayer, we are able to change from one kind of twins to the other by changing the position rate, and also by suitable post-annealing. We can align and induce change by applying a mechanical stress, both during growth and after growth. And after growth, we can still modify the microstructure of the system by post-annealing, by bending, and also by heating the material and making it pass the Martensitic transformation in applied field. Here there are some, in this case, magnetic force microscopy measurement of these materials. And the main message to take home is that the flexible Martensitic microstructure of these materials can be tailored in several ways, both during growth and after growth. And also the magnetic patterns can be obtained by applying external stimuli. The local application is very promising for easily tuning the microstructure and obtain the suitable micromagnetic configuration of these materials. On the other hand, thin films are a very good model system for study the structure of these materials from the atomic to the micro scale, and also to the micro scale. And by taking advantage of a film where we had both microstructure X and Y, so both kind of microstructure, we have made an experiment in eye field to study directly the role of the two different microstructure on the Martensitic transformation. And we have made a magnetic force microscopy imaging experiment in a magnetic field up to 14 Tesla and in a temperature range close to the transition temperatures, following these paths in iso field measurements by changing temperature and by applying a field at a certain temperature and inducing the crossing and inducing the transformation. Maybe it should work. Okay, you can see that by decreasing temperature we obtain the Martensitic transformation, and appears the Martensitic features of these materials. First, the Y-type Martensite, and then the X-type that is along the 45 degrees direction. Here now we are heating and cooling down, maybe. Okay, it has gone once and it's fine. The second, now it doesn't work at all. Let's see, no? Non va più avanti. Maybe it's a heavy file and, aspetta. Okay, this is the second experiment. In this case, we have applied a magnetic. Ecco. No, no. Yes, we have applied a magnetic field at 323 Kelvin and in the austenitic phase, and by applying the magnetic field we cross the magnetic transformation temperature, the Martensitic start temperature, and we obtain the Martensitic structure by applying the magnetic field. And in this case we have not obtained the full transformation due to the very high field needed to obtain this full transformation, but we have been able from the different images to write and derive an isotropy, the Martensitic transformation curves for both the different microstructures. And we have seen that the different twinning configuration show different transformation behavior, and that the width of the hysteresis that has to be reduced as much as possible is 25% narrower in the one kind of microstructure than in the other. And also for, in this case, the transformation rate for Y-type is much higher than the transformation rate for the Y-type. So we have obtained some results that can be exploited for many kind of metamagnetic Heuslers, and can be some kind of microstructure can be induced or favored to reduce the hysteresis of these materials. As last slides, I show you the patterned film. In this case, we have obtained the patterning of these materials in collaboration with the Institute of Metrology of Turin in the group of Paola Tiberto, and we have exploited nanosphere lithography, and that is the self-assembling of nanospheres of two different sizes. And what we have obtained, that the patterned film has exactly the same properties that can be exploited for the functional application of these materials. We have Magnetic properties, the difference in the hysteresis is also due to the magnetizing effects. And also we have a Martensitic transformation that is preserved in this low scale material that in this case are around 650 nanometers. We have a change in microstructure at the edges of this material from Y type to X type. We have also obtained smaller materials and checked the properties of the materials and also studied microstructure. And we have gone on with this research and to make a more general research, including study the effect of geometry and size of patterning. So we have used electron lithography and also optical lithography, UV lithography. In this case, we have obtained materials up to 3 microns with different shapes. And by checking resistance of these materials, we have found only a minor variation of the crystal transformation at, as a value as a function of the lateral size of the material. And we have nicely found also a selection of the orientation of between boundaries depending on the relative orientation of these stripes along the substrate. And we have reduced the size by electron lithography. In this case, we've seen big effects by reducing size on the Martensitic transformation. We have a reduction of hysteresis by reducing the size, but an increase of the range of the transformation. This it's more broadened, and an increase of the transformation temperature. Here we are making now some model, and we have involved some groups because we have to take into account many aspects, including surface energy of these materials, and we'll try to model the effect of this, all the terms in this behavior. So we have seen also the effect of lithography patterning. So we change microstructure, and we can also select a kind of microstructure by geometry. And as last, I show you some result that we have obtained, but this is a direction that is interesting for us, and let's see that this topic has inspired in our idea to detach the ferromagnetic shape memory thin films from the substrate. And the idea is to have materials that can be used for some cancer therapy, and in this case, it's cancer therapy for induced by the rotation of magnetic materials that activate mechanosensitive cellular function in a low field and low frequency. And there are some proposal of these materials, and in permalloy nanodisks, synthetic antiferromagnets. And in our case, the idea is to exploit of course, the possible tuning of the orientation of the magnetization, as we can do, but also if we can exploit at the same time also other multifunctional properties, such as the change of shape of these materials and induced by temperature or magnetic field. And in the prospect to make a new generation of micro and nano actuators made of multifunctional magnetic shape memory materials. As for the freestanding nanodisk, we have made a measurement in applied in TM at different temperature, and for these materials we have seen that by heating and crossing the transformation in external field or in zero applied field, we can tune an increase of the areal, or a positive areal strain or a negative areal strain of these materials, depending on the application of a magnetic field. So coming to my conclusion, what I wanted to point out is that the flexible Martensitic microstructure can be tailored in several ways, both during growth and after, by the application of magnetic field, of heat treatments, and that the local application of temperature or of stress and of magnetic field is suitable for tuning the microstructure also locally. The size reduction and geometry have a strong impact on the Martensitic twinning configurations, and looking at the Martensitic path, different microstructure have different transformation behaviors, and the hysteresis depends on the kind of microstructure. And so the magnetic flexibility of these materials makes them a very interesting and promising class among magnetic materials for the demagnetization of magnetism, for many, as a general purpose, for many kind of magnetic investigations. And the freestanding multifunctional nanostructures have a great potential for the realization of freestanding microactuators. I have finished, and I would like to thank all our collaborators, and in particular Milad Taksha Gafaroki and Greta Cavazzini, that are the PhD students who made a lot of these works, and Francesca Casoli and Lucia Nasi, that made of my group. Lucia makes TM, and Francesca magnetic measurement and magnetic materials preparation. And our collaborators at Parma University, at Darmstadt University, and in Zaragoza, the Laboratorio de Microscopía Avanzada, and the MUSP Institute, the National Institute for Meteorological Research, and the group of Paola Tiberto, and the big work done together at CEITEC in Brno with the group of Wojtek Ulier. And I thank you for your attention.
Thank you, Franca, for a very nice talk. You know, these kind of materials just set off your imagination and where you could use them. So, very nice work.